we can, okay, we can start in this moment, I think, yeah?
Okay.
Yeah.
Yes.
Well, it's my pleasure to present first speakers is Professor Roth and Professor Danielewski. And the title of the talk is Quaternion Quantum Mechanics from Hamilton SpaceTime to the displacement for potential in Planck-Kleinert crystal. Please go on. Thank you.
Thank you very much for letting me speak here today. Thanks to the organizers and a special thanks to Marek. It's a great honor. I would like to talk about three ideas today. First, how can we use quaternions in quantum mechanics to derive the Schrödinger wave equation? And why would anyone want to use quaternions? Second, how does this give us an ontic interpretation of quantum mechanics? And what is the reasoning and motivation behind this? And third, how can this be visualized? This presentation is based on a paper by Marek Danielewski and Luc-Jean Zappa that was recently published. And at the end, I will give you a short idea of what we are currently working on. Let's start with a visualization. This is what I will try to explain to you today. And by the end of this talk, I think you'll know exactly what this is. A brief overview of the presentation. In the introduction, I will try to convey the motivation behind this, why we think it makes sense to work on such a topic. Next, I will introduce the Planck-Kleinert crystal. Then I will try to convince you that quaternions are actually quite practical. Next, I will dive deeper into the topic and try to explain to you the main ideas, including how we can derive the Schrödinger wave equation and some other equations. And finally, if time permits, I will give you an idea of work in progress, including a simulation of spin 1/2 of 1 and 2 particles. As you all know, there are many interpretations of quantum physics. Most of you know the Copenhagen interpretation, in which case the wave function is not real. It's just related to probabilities. And the wave function is said to collapse upon measurement immediately. Then there are, let me show you the laser pointer maybe. Then of course there's the Broglie-Bohm interpretation, which is a pilot wave, sometimes it's called pilot wave. In this sense, there is a real wave, but there's still a particle involved. There's some other interpretations, and I'm sorry if your favorite interpretation is not there. I think we can all agree that nobody really agrees. And that's why we think it's worthwhile to investigate this topic. Now there's another interpretation, the neoclassical, and it's not much talked about. In this interpretation, it is a realist interpretation. The wave is ontic, the wave is real, and there are no particles at all. A few quotes from selected scientists. Murray Gell-Mann, he got a Nobel Prize in elementary particle physics. He said, Niels Bohr brainwashed a whole generation of theorists into thinking that the job of finding an interpretation of quantum mechanics was done 50 years ago. And maybe this is still true today. Even Schrödinger, the famous Schrödinger, he did not like the probability interpretation at all. He always considered it to be a real ontic wave. He said, let me say at the outset that in this discourse, I'm opposing not a few special statements of quantum physics held today. I'm opposing, as it were, the whole of it. I'm opposing its basic views that have been shaped 25 years ago when Max Born put forward his probability interpretation, which was accepted by almost everybody. So he wasn't happy about this. Now, are there systems that are well known that are classical? Let's look at some of these. Maybe you have heard of the word phonon. Sometimes you read in the literature, it's referred to as particle of sound or particle of heat. Phonons are spontaneous vibrations of atoms in a crystal lattice. They are studied in condensed matter physics. It's classical. So we are talking about a real crystal that vibrates. And interestingly, these vibrational modes, they behave similar to particles. They're also called quasi-particles. They behave like bosons, just like photons do. There are a lot of similarities between photons and phonons. Both are bosons, both are quantized and behave like particles or as wave. They have the same description in terms of quantum mechanics. So given the similarities, doesn't make you wonder if maybe photons are more similar to phonons than we may think. And maybe this is not such a crazy idea. There are numerous papers on double slit experiments and interference experiments with phonons, plasmons, and polaritons. Now, all these are quasi-particles. Now, all these are classical. That means we can see these waves. You can look at them in the microscope. So it doesn't require consciousness to collapse a wave function. It doesn't require the universe to split in multiple other universes, right? This is very simple. And so the question is, given that we can do the same kind of experiments with these quasi-particles, is it really, are photons really so different? Maybe it's not so crazy to at least think about that maybe it's not so different. The wave function collapse of phonons has been studied as well. The quantum mechanical properties of phonons in a one-dimensional lattice are studied with the conclusion that the phonon behaves in all essential respects as a normal quantum particle. So this could be an interesting system to think about what a photon actually could be. The next piece of puzzle is Minkowski spacetime. As you all know, special relativity and general relativity are usually described using a spacetime which is an interwoven continuum of 3 spatial and 1 time dimension. Now, in this model, gravity is caused by time curvature, and I don't have to explain this, you all know that. Now, what many of you may not know is that there is a mathematically equivalent model initially developed by Planck-Kleinert. What he did a simple coordinate transformation where instead of space and time, we use space and density, and everything else is the same. You can imagine this literally like an elastic solid, like picture him like a grid or a crystal. Whenever there's a lot of matter in this model, it changes the density. So gravity in this model is actually optical refraction. It's an optical mechanical analog to general relativity. And you may think this is crazy, but there are actually a lot of researchers using general relativity to study optical phenomenon. They use the metric tensor to calculate optical behavior in condensed matter. And if you're wearing glasses, you know what refraction is. So here's a simple example you can even do in your kitchen. You can take some bowl of glass and put water in it and sugar, you create a sugar gradient. Now, this creates an optical gradient refraction. And when you shine a laser light through it, it will actually bend the laser light. This is an example of how a gradient of refraction can cause a light to bend. There's some more sophisticated examples and analogs in optics. There are multiple papers on this. This one is from Nature. So on the left side here, this is the experiment, and the right side is the calculation. This is an optical black hole. Basically, what they did, they have some kind of a metamaterial that has an increased refractive index. And as the light, goes through the medium, to the metamaterial, it keeps bending more and more until it's actually captured in the middle. So it's literally behaves like a black hole. And the formulas used are exactly the same. There are even black holes of sound, by the way. This is a picture of Planck-Kleinert, and a painter painted his famous world crystal. Of course, it probably won't look just like that. Maybe more like this. Oh, I have to change my mouse pointer here. This is a simulation of what this crystal might be. So before we go into more detail, what are the properties of such a crystal? Well, we model it as a face-centric cubic crystal. It has dimensions, or the Planck length, as you can see, very small. Planck mass is the mass of such a particle. Now, keep in mind, when I say particle, this is obviously not a particle like we talk about with normal matter. This is, think of it more as a grid system in an abstract sense a little bit. So what can we say as a summary about this Planck-Kleinert crystal? Well, it is essentially the fabric of space-time, except here we use space density. Imagine it like a 3D coordinate system. And the fourth dimension is density. It has grid size, Planck length. It is an elastic solid, which can have deformations. It can have compression and torsion deformations. And there is an optical analogous model of gravity. It's basically refraction. Even Maxwell talked about this. He said, the assumption, therefore, that gravitation arises from the action of the surrounding medium leads to the conclusion that every part of this medium possesses, when undisturbed, an enormous intrinsic energy, and that the presence of dense bodies influences the medium so as to diminish this energy wherever there is a resultant attraction. As I'm unable to understand in what way the medium can possess such properties, I cannot go any further in this direction in searching for the cause of gravitation. And also Einstein thought about this. So in 1920, he said, more careful reflection teaches us, however, that the special theory of relativity does not compel us to deny ether. We may assume the existence of an ether, only we must give up ascribing a definite state of motion to it. Recapitulating, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without an ether is unthinkable. For in such space, there not only would be no propagation of light, but also no possibility of existence for standards of space and time, measuring rods and clocks, nor therefore any space-time intervals in the physical sense. Now, I'm sure some of you will say, well, hasn't this been disproven, Michelson-Morley experiment? And, you know, what doesn't that mean there's a absolute frame of reference? And what about special relativity? So if there are any questions about this, at the end, I have a few slides. If there's time left, I'm happy to go into this to explain a little bit more. So now the quaternions. Why would anyone want to use quaternions? Now, you all know what quaternions are, so I don't have to explain this to you. But for those who don't, you know, in airplanes, we use a gyroscope, which uses is a measuring device for measuring the location, the orientation of an airplane, for instance. Now, what can happen is when you rotate, when you flip the airplane 90 degrees, you get something called a gimbal lock, where the two axes actually interlock with each other, and then they move together, which is a problem. And this actually happened in Apollo 11. They even had a special button there in Apollo. And it happened. They had a gimbal lock in the mission, and they had to steer manually. Now, with quaternions, this doesn't happen. So quaternions are used a lot actually in computer graphics, in robotics, in navigation, in, you know, visual, if you're a game developer, for instance, everywhere where you have to deal with rotation in space. For instance, when you want to move a camera in a scene to another place, it's not just translation, it's also rotation. So basically, the laser pointer. Basically, you know, the first one is a scalar. The other three determine the axis of rotation. So it's very visual in a way, and whenever you have rotations involved, it really helps use quaternions. Who actually invented them? It was actually Sir William Rowan Hamilton. The history goes that he was working with 3D operations, but he was using vectors, and he got stuck with it for years because he just couldn't figure out how to get this to work. You know, he was wondering about introducing a second complex number, but it just didn't work. And it was said that he was walking across this program bridge with his wife, and suddenly he had the idea, oh, we have to use a third complex number. And he was so worried that he would die of a heart attack right there. He actually carved it into the bridge so that if he would die, this knowledge would not get lost. Now, if you think about this IJK, some people find this weird, but when you think about this as terms of rotational axis, it's actually not strange. So each one is just an axis of rotation. So you go I is 90 degrees, and then J, and then K. it's obvious that you go to -1. So when you look at this in a geometrical sense, it's actually quite straightforward. Now you all know that there are only 4 division algebras. The reason I mentioned this is there is no division algebra for vectors. There's no division operation for vectors, right? So it's kind of clumsy to use dot and cross product. Now, unfortunately, in physics, a lot of things has been derived using vectors, which is a pity because quaternions would actually be better suited for that. So also, Maxwell recognized the importance of quaternions. He said, the invention of the calculus of quaternions is a step towards the knowledge of quantities related to space, which can only be compared for its importance with the invention of triple coordinates by Descartes. The idea of this calculus, as distinguished from its operations and symbols, are fitted to be of the greatest use in all parts of science. So actually, he tried to reformulate electromagnetism with quaternions, but he failed. Others tried also and failed. So people gave up for a long time. I guess people were just used to using vectors. So unfortunately, all of quantum mechanics has been built upon with vectors and matrices instead of quaternions, and we hope to change that. So let's go back to the crystal now. Let's talk about the deformations. What kind of deformations are there? So we'll be using the symbol U for the deformation field. And there's basically 2 parts. There's compression and there's twist. We'll be using the symbol sigma for the divergence of U and the symbol phi for the curl of U. Just a simple visualization. So the left side is compression and the right side shows you twist. In all these animations, I'm using this red dot. So basically, I have marked one grid element so we can see exactly the movement of that. That's what this is, just in case you wonder. So you can actually see what happens. And keep in mind, we're actually looking at this in 3-dimensional space. So let me just. So you have to imagine it's a whole field, right? I'm just showing a plane to make it simpler, but we're actually looking at a field. So it's 3-dimensional. Again, this is left side is compression. And the right side, you have twist using 3 dimensions, but usually a plane is kind of easier to see. So maybe you can kind of see where this is going because, well, Helmholtz figured out that you can split up a vector field into 2 parts. It's called the Helmholtz decomposition. He has proven that such a field you can decompose it into the rotational part and the divergence part. Now, the nice thing about this, purely based on definition, it's clear that the twist of the compression is 0, and also the opposite, the divergence of the twist must also be 0. And this comes in quite handy because you can, when you have equations, you can always eliminate these terms very easily. Now we also need to talk about Gauchy. Baron Augustin Louis Gauchy, he's a French mathematician. He developed the displacement mechanics. There are actually 16 concepts and theorems named after him, and he wrote over 800 research articles. He developed the mechanics of how to work with displacement fields. If you imagine you have in your room a big coordinate system with rubber bands, for instance, and the 3 directions, you have to keep in mind when you ever have a deformation, the whole volume has to stay the same. And also closed curves stay the same. So basically you don't rip anything apart. So you can do any kind of deformation, but it has to be continuous. The volume doesn't change. Essentially, you don't break the coordinate system and you don't create any knots in it either. So this is the equation of motion. Let me just, I think I have an animation here. Yeah, so again, this is just a simple animation of a 3D crystal, Planck-Kleiner crystal, the kinds of motion you might see there. And it's actually quite simple. So the acceleration is related to the gradient of compression and the twist of the twist. We will use this as a basis to derive the wave equations. Now, as you well know, vectors are really not suited in this because there's no division operation. It's actually much simpler to use quaternions for this. So after many attempts to construct an algebra in R3 vector space, Hamilton realized that he needed a 4-dimensional space to do this. And this is where the quaternions now come in. So there exists a deformation field sigma, such that one could represent the solenoidal, the vector, and scalar field as a superposition of real and imaginary parts at each point. So this is basically the scalar part, and this is the vectorial part. And now all we have to do is combine these two. It's really quite simple. And you have Helmholtz and you have Gauci, and now we just combine that. So let's again look at the equation of motion. And now all we do is we apply the Helmholtz decomposition, which means we use the diff and Roth operator, and then we see what happens. So when we apply the diff operator, what happens, as I told you before, based purely on the definition, right? All these red terms will go away because the divergence of the twist is 0. So this will go all vanish. Now, when you look at this, maybe some of you can guess what comes out of this. Well, when we do this, this goes away and we substitute the divergence of u with sigma 0, then what we end up with is simply longitudinal waves in space. Now, most people think of this as, look at it in a plane, but actually, again, we're looking at 3 dimensions. And again, imagine the grid, right? We're looking at the whole volume, the 3-dimensional longitudinal wave. Now, that was quite simple. Now we just do this again. We do the opposite. We apply the curl operator to this. And again, because purely based on the definition, we know that all these red terms go away because the twist of the compression is 0. So when we do that, we end up with this. And what do you think happens now when we replace this? Well, we get transverse waves. That was kind of obvious, right? So all we did now, we replaced the twist of u theta, and now we have transverse waves. And again, we're looking at this in 3 dimensions, of course, not just flat, so 3 dimensions. Again, this is the summary, what we did before. We have these 2 wave equations. Now, what happens when we combine them? I mean, we don't have just only transverse or only compression waves. When we add them up, we get all kinds of waves. So here's an example, and I wonder if some of you recognize this. I hope you guys do. I will tell you at the end what kind of wave this is. So as you can see, you can form many, many shapes of waves. A hint is the red line here. Maybe you can see what this red line doing. So again, this red line marks 1 grid point, and you can see what it's doing. Now we need to also talk about the energy of the deformation field. So here, this is the equation, and both the equation of motion and this equation, they obey the Euler-Lagrange relation. So you can imagine this is sort of like a pendulum where the energy is either in the kinetic or in the potential energy. In this case, this would be the u dot, that's the velocity of a 1 grid element. So when I play this, you can see that red dot, that again marks 1 grid element. You can see that the energy, when the velocity is high, there is no strain. And the opposite, when there's no strain, there's high velocity. So it's like a pendulum. And again, it is Euler-Lagrange relation. And what's important here is also when you look at the span of this, so that the maximum kinetic energy is the same as the maximum of the strain energy. Now, when we start to think about Schrödinger and all this, I'll get back to this later, and I'll talk a little bit more about this image. So what we can do now, so the energy equation acts as a local boundary condition. And what we can do, we can rewrite the equation of motion as a multisystem. And now we end up with 2 equations. The first one is the Klein-Gordon equation, which is well known. It's a relativistic wave equation. It's Lorentz invariant. Now, I wonder if you guys recognize what the second one is. What we can do now, since we're actually working with a real elastic solid, we can put in the values of the Planck-Kleiner crystal, Planck mass, the length, the Planck time, and so on. And we do that, and we do the substitution here. Then we can express this as a function of the local mass density. Now, maybe you recognize this now, what this looks like, because when you look at this part, this is actually G, the gravitational constant. So it's very interesting that we are able to derive the gravitational constant from this model. So this is the result from using this elastic solid model in Gauci, and this is the official NIST. These are NIST values. Of course, these values change, because it's not super accurate. You can see that the values changed from 2006 to 2014, but you can see how close it is. This is actually very close. I think that's pretty cool. Here is a summary of several other physical constants of this Planck-Kleiner crystal. Now, what I find interesting, the Young modulus is really, really high. If you think about it, I think a diamond, it's around 10 to the 12 or something like this. So this crystal, you have to imagine, it's very stiff. It's much stiffer than diamond, which is pretty interesting. And using the Young modulus, you can actually calculate the speed of light. So again, this was calculated using just this model, which is, I think it's pretty cool. So let's get back to the energy, because our goal is to calculate the Schrödinger wave equation. So it has to do something with energy. So to do this, in this model, the energy, we have to look at a certain volume, because what is a particle in this model? There are no particles. So the particle really is just a volume, the energy contained in a certain volume, okay? Obviously the energy is constant, and also for the derivation, we assume it's mostly stationary, so it doesn't move around at relativistic speeds. So what we have to do, we have to calculate the integral in this volume of this energy. To do this, we'll need an operator D, which acts on quaternions, and actually it corresponds physically to the gradient in 3D space, which is kind of cool. So this directly connects quaternions to the elastic solid, to physical reality. So all the calculations we do have a physical meaning. We also need the normalized velocity. That's not a trick. And of course, please, the details are in the paper, because there are several pages and I have no time to put this all, yeah, so the normalized velocity is equal to the normalized gradient of the mechanical potential. Now there's a few tricks. So we take the energy of the deformation field, we calculate the integral of a certain volume. Then there's a few tricks we do. So we replace these terms with phi, and you can probably guess why. Then we use the normalized gradient of mechanical potential. Now the mass here, you wonder about this mass. This mass is now ontic. This mass is basically the energy of the system divided by c squared. So there's no particle. Again, it's just the energy in that volume. And so there's a little tricky part, which is explained in the paper a little bit more. It's you have to use the Dubois-Raymond lemma to do this. And maybe you recognize this already. What we can do now, we can replace these constants with h bar. And this lambda is actually, it's a multiplier, so you might as well use energy here. Energy. When we do this, we get the time invariant Schrödinger equation, all with quaternions. So let's compare a little bit the Schrödinger equation with the complex, the traditional Schrödinger equation. And there's only one major difference. The complex Schrödinger equation, you have the complex I, and which is kind of weird, I think, because we're operating in 3D space. So to me, it's much more logical to use 3 complex numbers, because you're looking at a 3D space. So that's the main difference. Now you may wonder if this is really compatible, but actually it's quite easy to see that you can convert a quaternion back to a complex number, but simply by projection. So here on top, we have the mechanical potential, the 4 potential of the quaternion. And at the bottom, we have the same thing for the classical quantum mechanics. And it should be easy to see that, you basically can project it down to a plane. So in summary, in this model, the wave function is real. It's ontological. There are no particles, none. There is just all waves, and everything we call particle is basically quasi-particles, or it looks like particles. It's quantized energy and so on. It's energy is pure wave energy. The mass is related to the overall energy in a certain volume. Now, of course, you may wonder, well, what's next? This is just the beginning, okay? Obviously, we'll have to. The next step to me, obviously, is the direct equation and spin 1/2. Now, why is spin 1/2 important? Well, because protons, neutrons, electrons, they all have spin 1/2, and it's the source of the Pauli exclusion principle. And most of you probably know what spin 1/2 is. It means you have to rotate something, and it returns to the same state after 720 degrees. And the direct equation describes that. So we really need to understand spin 1/2 in the elastic model, because if we can't do it, then the model is not going to work. So in case you don't know what spin 1/2 is, here I have a short simulation. You can try this yourself. So the goal is you take a cup and you rotate it continuously. You can't spill the coffee. You can't move your fingers. You can't switch arms. You can't get up either. So I don't know if I can do this here. So the trick is, of course, you have to twist your arm a little. It's a little bit small space here. So when you do this about 100 times, then in your head you can visualize. Oh, it's going better now. Okay, so this is spin 1/2. So what I was wondering, can we visualize this in a computer simulation? So to make this more understandable to people, and yeah, so I wrote this. It's a simulation in Unity 3D, C#. You can actually zoom into this and fly around. So this is spin 1/2. Again, there's one grip point that you can see how it's moving, and I added this sphere only so that you can see the rotation better. And again, this is of course not, and it doesn't tear apart space. So this is completely compatible with it doesn't create knots. It doesn't tear apart the grid or anything. And again, this is 3-dimensional. So here on the right side, I added a second plane so we can see. Here's a close-up. So maybe you can see better. What you'll notice is that the sphere appears to rotate. The sphere appears to rotate twice before it gets back to its original situation, basically. So this is spin 1/2. So this is perfectly compatible with an elastic solid model. Here I removed the sphere, so you can follow the vector. There's a little tiny symbol. It shows how this grid element is moving around. We can also do this with 2, actually. So now what's interesting about this one is, so I have, again, the sphere is only for visualization purposes. There is no sphere, okay? This is just to help you see. You notice that the spin is opposite. So one is spin up, the other one is spin down. And the reason for this is in the middle or so, I'll switch it to equal spin. And you can see that this is not compatible. If you have 2 particles the same spin that get too close to each other, it will rip apart. It's not compatible. So this one will create, it doesn't work, especially when they get closer together. You can intuitively see that it will create a mess. So now they have equal spin, and you can see it creates a mess. So it needs to have opposite spin. It's a very simple visual, intuitive understanding of why you need spin up and spin down. And of course, with this model, we can create much more complex spinners. Not just that what I showed you, but any combination. There's many ways how you can create spinners with this model. But again, it's all compatible with the elastic solid model. So I hope I was able to motivate you a little bit to look in this area maybe, and hopefully other scientists will join and to do more research in this topic. So I want to thank you very much for your attention. And I also want to mention other researchers. So several will follow, but Ilya Schmelzer and Robert Close are not able to talk today. And I hope if you're interested, you will also consider looking at their research. Thank you very much. Are there any questions?
Oh, thank you very much. Thank you for presentation of such a number of physical and mathematical ideas and presentation of models of these ideas. And do we have some questions, please?
Well, I raised the hand. Can I?
Yeah, can you?
Okay, Radek, so it's very nice talk. As I understand, your model of particles is like you have some small volume and you integrate energy momentum tensor and energy inside it.
It's like a stationary wave. Basically, the wave energy is like a soliton wave. So we have a stationary wave, right?
Yes,
you can imagine this in a certain volume. Now, when we integrate over this volume, we know that what we call particle, it's in there. So in the whole energy in there corresponds to one particle in quotes.
Yeah. So that's why how I understand it. So, but this model is quite similar to the approach of Schwinger. He forget about particles because for him particles were very nasty construction.
Yeah.
And he instead take energy momentum tensor and integrate over the volume, and he instead of particles considered currents, and currents are the basic construct in his theory. So I think it could be somehow connected with his ideas, at least in my understanding of your theory.
Yes.
Okay. Question.
Thanks.
May I speak?
Oh, yeah, I see lots of hands. Do I need to call out or?
I have a comment
Yes.
to your lecture. May I speak?
Yeah. I want to give
My name is Danielewski. As an old relativist, I cannot agree with you that in general relativity, space-time is rigid. Contrary, it is an elastic body. Its geometry is dynamical. My second remark is that, as I remember many years ago, specialists on so-called continual theory of dislocation in crystals, for example, Kleiner, discovered very big similarity between this continual theory of dislocation and general relativity. This observation led him and, for example, Professor Kell from Kell to generalization of space-time model from Riemannian manifolds, pseudo-Riemannian manifolds with metric Leibniz-Vita connection to more general Riemann-Cartan manifolds, this metric manifolds with torsion. You have told about
yeah, I can also, in case you want to wonder about special relativity, I have a slide too on that, in case anyone has a question about that. Manfred?
Yes, please. Do you hear me?
Yes.
Because my microphone sometimes is switching off. Oh, it's working. So I have first. So can I speak?
Yeah.
I have first a comment concerning quaternions. I like them very much, and but they were invented by Rodriguez in 1840.
I actually read your paper. Yeah, you're right.
Yes.
Yeah, you're right. 3 years earlier, but I saw that too late. You're right, actually. Yeah.
Yeah. Okay, so I have a question, and you mentioned that you can calculate the speed of light. For me, speed of light is something I can naturally constant, and it's so how do you really derive speed of light, or on what does it depend?
Oh, okay. Well, it depends on the material constant. So let's just pretend we're looking not at space-time, but just another material. It's easier to talk about, so maybe there's less conflict. So in any material, maybe I can show this, right? Any material you have, water, whatever it is, you have a speed of the wave speed. Let's call it the wave speed, okay? The wave speed is constant in that particular material. Let's just forget for a moment about space-time and all that. So now we have to imagine a world where everything is composed of waves in that material. Let's take a phonon world. You have a crystal with phonons in there, and there's this phonon clock. So what this is you have a little phonon wave, okay, that moves around the circle, and that's one click, right? No problem here. Now, this speed of light, in this case, speed of that wave, is constant throughout that medium. Okay, it's in an absolute sense. Now, what happens when we watch as godlike observers? We watch what happens. Now, let's say we move this phonon clock, right? This phonon clock is now moving, actually downwards. Sorry, it's moving downwards. Now, what happens is the path is getting longer as the phonon clock moves. Now, the thing is, the speed of that wave is constant. So that length is the same as that length. That means it will not get all the way around. That means this phonon person wearing this phonon clock will think that time is actually slower. So when they get back later together, they meet up, they will count the clicks, for instance, how many clicks were passed on their clock. They will see that, this clock had fewer clicks than this one. And it's simply, so basically special relativity is a property of any wave system, So now in our case, we are composed of waves. So everything, electrons, protons, we are waves. Photons are waves, our measuring sticks are waves. So if you think of that, then it's actually obvious that any moving system, any clock we have is composed of waves. That has to tick slower because the path if you move it, it will be helical, it will get longer, it will stick slower. It's actually so simple when you think about this. But I know people always think, oh, it has to be more complicated, but actually I don't think it doesn't have to be more complicated. What do you think about that?
No, so you don't derive the speed of light in vacuum. You say
Oh.
it depends on the medium, on
Yes,
masses
on
and
the,
so.
the,
You
the
have
Young
the
modulus.
dependence.
Yeah, maybe Marek
Pardon?
can also talk about this. It depends on the Young modulus. It's the square root of Marek, you know better, the equation
Yeah, yeah.
for deriving
it
the speed of
Depends
light
on
is,
stiffness and such things. It depends on stiffness and,
yes,
properties
exactly.
of medium.
Young
Yes,
modulus
yes.
is really high. It's 10 to the 114, so it's very super stiff, as you can imagine. Otherwise, the speed of light wouldn't be so quick.
Yeah, yeah. Okay. Thank you.
So thank you very much.
Can I, Marianne? Okay, good. We're being recorded again. Marianne Kupczynski wrote, Chantal, are you a wave also? And that's actually my question now to you, because you used a word in your talk. You said this is ontological, and you meant the waves. But in in the real world, there are tables and chairs and people. And in your world, there are no tables or chairs or people. So I think you should not use the word ontological.
I see them
These these waves of yours are in our imagination. Okay, and they're in our mathematics, and they may give good predictions, but they are not the last word. In fact, they're only an interface to predictions about what actually happens in the real world, like the moon being there or not being there, and so on. So this was my remark to you. And it was a beautiful talk, beautiful pictures to movies.
Well,
too.
actually, when you zoom into the chair, right? The point is when you zoom, if we were like godlike beings, we could do that and look at all the way in detail. At the end, what we would see if we were godlike beings, we would not see any particle. We would see the waves. So that's
no, we wouldn't see the waves.
Well, we cannot because we are human. We are made of waves. But let's say there's a phonon universe.
I don't know if we're made of waves. We can imagine we're made of waves, but I think this is
in this model. In this model, we are all vibrations. So imagine there's like a big crystal with phonon worlds, phonon people, and phonon chairs. Yeah. You would zoom in there with a microscope. You would see the wiggling of the crystal, right? That's in a way. That's what we. It's an analog model, basically.
Yes, so, in the model, yeah.
Yeah. Well, we think that it could be actually the model. It could actually be, the way. So the universe could be a big, elastic, solid. I know it sounds strange, but.
Well, maybe it could be really, but I still think that actually, if it is, it's still only half of reality. And for instance, you mentioned the work of Ilya. Mm-hmm. I forget his surname.
Ilya Schmelzer.
Yeah. Who says, well, okay, I mean, we can bring back reality and have particles and cliques as well, and have a preferred reference frame, and bring back reality, bring back ontology to everything. Yeah. But we have to accept action at a distance then.
Well, we can talk about this. Is a whole big topic, as you know. Yeah, sure. We'll set a conference just on that. Yeah, totally. I agree. There's some issues there. Yeah.
Okay. Thanks.
So thank you very much. Who else?
Can I make one question?
Sure.
Okay.
So there is a model of, there is a famous Volovik book, The Universe in Helium Droplet. So he somehow also models the space-time in, so actually the metric is encoded by different order parameters. And there is like mapping of Bogoliubov-Dijen equations to curve space-time, right? Mm-hmm. So did you make attempt in this direction with this quaternionic model? And do you have extra possible predictions that were not accounted from previous models?
Well, this is work in progress. So we're actually thinking about what the next steps are. So maybe if you have some pointers, we could try to go in that direction. We are actually open for ideas. And also if anyone wants to collaborate maybe and has, can help us.
All right, thank you.
One other remark.
Okay.
In relativity, we have no ether. We need no ether.
We don't need it. That's true. We don't need it. Yeah, that's true. We can never detect it. We don't need it. So it's just like when you have sound waves in air, you don't need the air to calculate, the Doppler effect. You don't need it. but it doesn't mean it's not there. So even Einstein said, you know, it makes sense to consider it. It's just you can never detect it. You cannot. It doesn't have a movement in itself. But it's not it's not a problem in terms of the mathematics. Is exactly the same.
Relativity excluded notion of ether.
Yeah, but it's just you don't need it. But even if you have it, because special relativity, it's basically a wave. It's any wave system will automatically have special relativity, and you don't need it, right, to calculate anything. You would, because actually, you know that the Lorentz, the Lorentz factor actually came from Lorentz, and he actually had this initially. They were actually using the ether to calculate things, and they realized, oh, it's way too complicated. So then they figured out a way how to do this without ether. But it doesn't mean it's not there just because you don't need it.
May I have a word? It was a question about future. Future is in every direction is unsolved. There are unsolved problems. Density functional theory. Obviously, using quaternions, we will be able to substitute several constants introduced over the years for accounting different interrelation between particles, whatever, by this theory. Of course, what will be final results is difficult to say, but surprising are accuracy of the physical constants obtained by using this model. You can verify everything. Just everything is agreement. Next direction, Chantal already said. Dirac. She didn't mention about it because paper is now under revision. So it would be before. Another interesting Klein-Gordon equation. Again, it's much more rich. Quaternion Quantum Mechanics is much more richer and in agreement with all the results. There are no contradictions. Several of you asked about general relativity. I will memorize one. Planck-Kleiner, what he really did, he assumed basically the same with some special constants, but he introduced defects. Defects that were generated by mass, especially high mass densities, like star, whatever. These defects, they deform space grids, as Chantal was saying, and this creates gravitational interactions. According to this situation, what we did is situation is even simpler. We don't have to introduce defects. In fact, energy itself deforms space and creates gravity. But basically, concepts are the same. What Kleiner did is, in fact, he obtained general relativity equation in agreement, which is in agreement with Einstein equations. Exactly the same expression. Yeah. Exactly the same. I believe another very interesting direction. Chantal said about this by introducing deep refraction around big mass, star, whatever, and by inversing the geometry, we obtain. Yeah, I believe we will obtain the same equations. At the moment, we have simple, childish, you may say, Newton formula for some equation. But next step, I'm completely sure, but I'm not a mathematician. I cannot do this by myself. Somebody has to spend some time with this. But obviously, for me, results will be very similar to Planck-Kleiner, which means general relativity. So what we did, in fact, in this simple few papers, we combine quantum mechanics with gravity. At the moment, in the simplest form. Thank you.
Thank you.
Thank you very much. Well, who else?
Last remark, if possible. In relativity, because we have no ether, then we also have no absolute frame of reference. All frame reference in relativity are equivalent and are Lorentz invariant.
Sure. Yes, I'd be happy
you-
to. I have several papers I can send you if you like the link, because this has been derived before. So people have derived, special relativity based on a model with an elastic solid model. So that's actually not new. And yeah, we can never detect it, but it doesn't mean it's not there. We will never know about it. We never know exactly what that frame of reference is. In a way, the fabric of space is the same, right? Whether you use space density or space time, in fact, that gravity bends space time, you are still actually kind of talking about an absolute frame in a way. In a way, it's kind of similar.
Okay, who else? Oh, so thank you very much.